This is Yuewen. Fang. I'm from China. I'm a computational material scientist. Daniel. Daniel is a computational physicist for cosmology and for materials. And computational physics is a combination of the physics and mathematics and computational and computer science. Briefly speaking, we are applying numerical methods in computers to solve the problems in physics. I started to do the computational physics during the undergraduate study in central China. And I got a national research grant which can support me to do any research I'm interested in. I thought like computational physics is very amazing because not only I could learn physics, but also learn mathematics and computer science. So I chose to do the molecular dynamic simulations for the carbon nanotubes. And I studied the melting and pre-melting process in carbon nanotubes. After that, I got a PhD scholarship in Shanghai, so I moved to Shanghai and joined the East China University and the New York University Shanghai campus. There, I started to use the first principle quantum mechanical methods to design materials. For example, the ferroelectric materials that can be used in sensors and memories. We predicted some new ferroelectric materials and proposed some memory device models. Indeed, some of the predictions have been confirmed. For example, the Lanthanium tungsten nitride has been fabricated by the US scientists last year, which demonstrates the power of computational physics. I spent the latest years in Japan at the Japan Ceramics Center in Nagoya and Kyoto University and Tokyo Institute of Technology. There I developed some software to use the high-speed method to accelerate the materials discovery and apply these methods to study the thermoelectric materials. Such materials can convert the heat into the electricity, and obviously it's useful because it can be used to solve the energy crisis problems. And currently, I'm at the CFM in the Young's group. We are studying superconductors. So superconductors are materials like the electrical resistance are vanished under a critical temperature. Such materials have been widely used in the hospitals, like magnetic resonance imaging, and in some countries, like in Japan and China, there are some commercial maglev trains that can run more than 600 kilometers per hour. That is almost 2 or 5 times of the usual trains. And the most promising room temperature superconductors could be the hydride because they are relatively high critical temperature. However, as you can see in the left figure, if we want to achieve a relatively high critical temperature, we have to apply more than 170 gigapascal pressures. In the laboratory, we have to use the expensive material diamond, and this is the hardest materials in the world. We have to use the diamond precision materials to achieve very high pressures. However, such experiments are almost unavailable in most of the laboratories in this world. And in our current laboratory, we are using the purely computational method. Here I combine the high-performance computers and the high-speed structured screening method, and also the artificial intelligence method like machine learning method, as well as the state-of-the-art superconducting methods. Our objective is to find room temperature superconductors that can exist at the moderate pressures or even at ambient conditions. And I hope some of the contents could be interesting for you. If you are interested to know more, you can come to my booth 23, I have a poster and some demos for the molecular dynamic simulations and the first principles calculations. And basically, you can come to feel how to be a computational material scientist because we don't need a laboratory, we don't need the instruments. If we have a computer, we can be a computational material scientist. And thank you very much.